Hey, Jock here. It's time for information on topic 2, projectiles, otherwise known as 2D motion. Hope you have your notebooks out because we're going to talk about strategies. We're going to talk about two different examples, one I do, one you'll do, and you'll compare it to my result, as well as get a good understanding of what's going on when something's in the air, moving both forward and up and down. In the end, I'm going to give you a little link and let you play with a cool little simulation to help you think about different ideas, and it'll be a wrap. So here's the basic idea behind the entire topic. Is gravity a pull in both the x and y directions? And the answer is, of course, absolutely not. Gravity only pulls in the y direction, only pulls you down. Gravity does not pull you left or right. Because it has no effect in the x direction, when something's in the air, it has no acceleration left or right. It's only getting pulled down. So if something has got forward motion while it's in the air, that forward motion remains constant the entire time it's in the air until it hits. So if you shoot a bullet forward, it's going to keep on moving that same forward velocity every moment it's in the air. What's going to change, however, is its up or down velocity, which will change every moment because of gravity's pull. So here's our 5 strategies. These are going to be using constantly throughout the topic. And in fact, we're going to use them in the 2 examples we're doing today. So if you don't write them down, then you're kind of foolish. Strategy number 1. Separate the info into their x and y parts. Draw a picture number line to help you out. Seriously. A picture will save your bacon many times. So you're going to make a column just for your x information and a column or table just for your y information. Never put them in the same column, because if you start using x numbers with y numbers, you just pretty much broken the matrix. If something is at an angle, we're going to see soon, you have to break it up into x and y and then put those values into their little tables. Number 2, because gravity only acts in the y direction, that gravity of -10 value, which we talked about, is only the acceleration in the y. The acceleration in the x is going to be 0, because gravity doesn't pull you left or right. So in your little x and y tables that you're making, a is -10 for y, a is 0 for x. Number 3, key phrase. Horizontal means it only has forward motion at first. And since you're only moving forward at first, there's no up and down motion that first moment it's in the air. So the y initial velocity is 0. The x initial velocity is just that velocity it was thrown or shot horizontally. And since it doesn't change, it's just your overall velocity in that first moment. The y velocity will change every moment because of gravity. The x velocity will stay that constant. Number 4, time is not broken up into x and y. Time is just an overall value. So then if you get a value for time, it's for both x and y, so it's your link. And number 5, the last thing you're going to do as your strategy is to solve what you need. Usually what happens is you solve for time in one of the directions that you know the most about, and then use that time in the other direction to solve what you need. So here's our example. Can you please pause, copy it down with the same kind of general format, with the question, a little space underneath, space for the strategy, which would be really small, and finally the result, which would be the main part of the section. Do it, then press play. Okay, here we go. Here's the picture that I drew. You should copy it down as well. The key idea here is that the pelican in the first moment lets the fish go. The pelican and the fish share the same forward velocity. The fish will then take this little dotted path down and hit the water, or the nest, I should say, right here. What we learn from this is that the starting height of the fish is 20 meters, and the final height of the fish is 0 meters. And it starts off with a forward position of 0, and it ends up with a forward position of 8 meters away. So before you do any kind of strategy as well, the first thing you should do is look for key words and underline them. I noticed the phrase horizontal, which meant that there's no y velocity stuff at first, and it's forward, so that the forward velocity, the forward position is going to be positive. So first thing you do, separate out into your x and y parts, 2 separate tables, and here I am. Starting position 0, final position 8 meters positive. Y, starting position positive 20 meters, final position 0. Strategy number 1. Number 2, list the accelerations. In x, there's no acceleration always, unless there's like a rocket or something attached to it, but it's no longer a projectile, it's simply something that has its own motion. And then acceleration is -10 meters per second squared, because negative is down here. I know that because I said the starting height was 20 and the bottom height is 0. If somehow I said that this was 0 and down here was 20, this would be a positive value because I'd be saying it's going up. Complicated? So let's make it simple. When you go down, you end up at a final y position of 0. Number 3, the phrase horizontal. If it's used, use it. And here we go. Since there's horizontal motion here at first, the initial velocity for y is 0, and the initial velocity for x is unknown. We're trying to find it, because that's how fast the pelican and the fish were going that first moment. Number 4, the times are the same. So I'm going to write time equals time here. That's my reminder. If I find time, let's say, in the y direction, I could use that in the x to find what I need. And the 5th strategy is solve, so let's do it. Since I knew more about the y direction in this case, because I know not only the final and starting position, the acceleration, but I also know the initial y velocity, I'm going to solve for time using that information. I use this equation, you can see right here. I'm going to solve for time, and I get 2 seconds. Now I'm going to use that to solve for the velocity in the x direction. Same equation, this time I'm using only the x information. 8 equals 0 plus blah, blah, blah. I get initial velocity of 4 meters per second. Write that down, make little notes on how you have to do this. You're going to be doing this a lot. And analyzing what happens. And then when you're ready, let's go on. So you throw away, the strategy should be moved a little bit, I know. It should be in this little column. Ball horizontally at 2 meters per second. The ball starts up in your hand, which is 1.5 meters tall. So the ball starts off in your hand, 1.5 meters tall. You're throwing it at 2 meters per second. How far from you will the ball land? I would like you to now please pause, try to work this out, look at the previous ones if you need to, and then when you're ready, compare what you did to me, and I'll wait. I'm done waiting. Here's how I did it. First of all, the picture, of course. V0 is 2, 1.5 meters tall. Here's the projectile. So I redid this and made this little picture here. Initial velocity of 2. Starting y positions will be 1.5. Final y positions will be 0. And we're trying to find the final x position, assuming that it starts off at 0. Strategy number 1. Here's my table. Notice I put the x velocity in for the initial velocity here. Step 2, I put the acceleration in. Step 3, because it's going horizontally in this case, I can put another thing for y. Step 4, we're going to solve for time. We're going to use the y information again to find time because there's more of it. So, it's not a nice number. You probably have your calculator out. When I solved for time, I got the root of 0.3 seconds, which is also 0.547 seconds. And then using that in the x, I found the final positions around 1.094 meters. If you're looking pretty good and you got it, not bad. So what if you throw it up at an angle? Oh, geez, Jock. Well, it's doable. At an angle, all our strategies still work, but you just have to do one more step of finding the x and y parts of that initial velocity. So for example, here, you throw a basketball at some velocity, v0, at some angle, and you want it to go right through this hoop. Can you please now take a moment and make an x and y table of all the things you could assume in this case? Oh, I'll wait. Cool. Let's see what we have here. I said the initial velocity in the x will be this cosine of the angle, because cosine is the x in this case. And I said that the y is v0 sine theta. And both of these should actually have a positive in front of it, because the y part is going up, the x part is going forward. The other thing I could say, besides the accelerations, which are always true, is that in this case, the y position, it starts off here at 0, it ends at positive h. And the x starts off here at 0, it ends at positive s. So with these two things, and also the accelerations, you can now theoretically solve for anything you want in this situation. Cool. Now I'm going to show you one last thing. And that is right this conclusion. In situations where the object's in the air and has x and y motion, that's what we've been talking about, we have to look at the x and y parts separately, with time being the link between. And if you're finding an overall motion at some point, like for example, how fast is it going after 4 seconds, we have to combine the x and y parts at that moment only. And with this, wonderful students, let me show you a cute little simulation and you'll be on your way.